Hello everyone. In this video, I will introduce the use of Blender Bone Physics add-in, BoneX. First, let's go to the add-in panel. Select the armature we want to apply, enter pose mode. Select the bone you want to assign, then click the Start button. Press the C key. You can set the selected bone as rigid body. Now we select playback option. Start playback. Then the bone is affected by gravity, sagging and falling downward. But if we want this bone to move with your control, you can enter the bone editing mode. Parent it to another bone with Ctrl P. Now this bone becomes a child of that bone. Start playback again. You will notice a joint will be created here to connecting the physical bone. The physical bone will rotate and move around this joint. At the same time, you can also transform the parent bone. That completes a very simple physical bone effect. Now, let's take a look at the add-ins UI. After we click the Start Modify button, we enter the add-ins Modify UI. On the left, we can see many operations. The first part is for setting and unsetting physical bones. Select the bones, and press C key to set them as physical bone. But later, if we want to temporarily unset the physical bone, we can press the V key to unset. But after this V key cancellation, the parameter of rigid body still remaining in this bone, until next time you set it as physical bone. If you want to completely delete and clear these properties, you can press Ctrl-Alt-Shift-C. This will clear all parameters of physical bone. The second part is shape drawing. After entering the interface, you can view the shape of the physical bone. You can display its faces or edges, or hide them. The third part is the modification of the shape of the physical bone. You can scale the physical bone shape by pressing S. Scaling along the XYZ axis. Pressing the T key can switch the shape of the physical bone. The default shapes include a box and a capsule. If neither of these shapes satisfies your needs, you can press the E key to enter edit mode and modify. After completion, you can see its shape applied, but be aware that only convex polygons are supported during simulation. If you generate a concave polygon in edit mode, it will be baked into a convex polygon before simulation. Ctrl-M will copy the activated physical bone shape to other selected physical bones. This part is the use of soft connection. Soft connection refers to a spring between two physical bones. The soft connect links their displacement relationships, but does not link their rotational angle relationships. Another part is the additional constraints. Additional constraints mean that during the simulation process, although there are hard constraints, but they may still be exceeded due to large forces or some irresistible reasons. Then you can use the additional constraint added to the bone to make sure it is absolutely limited in your range. After adding additional constraint, you can see some bone constraints are added on the bones. These constraints can avoid physical bones be pushed away from the position it should be. Now we take a look at the parameter of physical bones. After we set up the physical bones, select the physical bones. Then you will see the corresponding parameter in the panel. The type of physical bones divided into kinematic rigid body and dynamic rigid body. Kinematic rigid body refers to rigid body being completely controlled by you. You can control it by keyframe animation, and it will not move under any external forces. The dynamic rigid body, which can move under external forces, and is also affected by collisions of other rigid bodies. Next parameter is the mass of the physical bone. Mass has impact on many aspects. First is the influence of inertia. This yellow line is a spring. Swinging under the same spring action. Comparing a 1 kg physical bone and a 10 kg physical bone. The 1 kg bone is more easily pulled by the spring, while the 10 kg bone, due to its larger mass, is harder to be pulled by the spring. Another impact of mass is the influence on gravity. A 1 kg physical bone under the effect of gravity only sags a little, while a 10 kg physical bone is greatly affected by gravity. Another very obvious effect is the impulse. In this example, when colliding, impulse conservation occurs. When a 1 kg physical bone collides with another 1 kg physical bone, it produces a faster speed, while a 1 kg physical bone colliding with a 10 kg physical bone, its resulting speed will be smaller. This is its impact on impulse. Another parameter of our rigid body is its damping. Damping represents the air resistance this physical bone experiences. The higher the damping, the greater the resistance it faces during its transform. Another parameter is its friction. Friction is divided into static and dynamic friction. The displacement of 0.5 friction coefficient is relatively more noticeable compared to 0.9. This is the impact of its friction coefficient. Another coefficient is its bounce coefficient. It reflects the rebound level of a rigid body upon impact. At point 2, the rebound is small. At point 7, you can see a very noticeable rebound. The physical bone has a very important property, which is their collision group down here. If you have a skirt and you want the shape of the physical bone fit the mesh of the skirt, the shapes of the physical bones may interpenetrate. In this case, we can use the group and the collision group to cancel its self-collision. A group explains which group this physical bone belongs to. Collision group specifies which group this physics bone will collide with. For example, in this case, I set the skirt's physical bone to the second group, and its collision group's second group switch to empty. This means it will not collide with itself. Then here is a chain. I also canceled the self-collision for the chain, but I set it in another group. Then after simulation, we will find that they can collide with each other, but their self-collision for themselves is cancelled. You can check the difference between group and collision group here. Next, let's look at the joint settings of the physical bone. When creating physical bones, this add-in will check if the physical bone has a parent. If parent exists, a joint will be created at the head of the physical bone, and the physical bone can rotate and move around this joint. There is a spring connection between the physical bone and the parent. Spring has two main parameters: stiffness and damping. The spring stiffness refers to how easily a spring deforms when subjected to an external force. The higher the spring stiffness, the harder it is to deform. Damping refers to the resistance of the spring to return to its original position. The higher the damping, the softer the simulation results. The stiffness and damping are the soft constraints of the spring. Down below here are angle limits and distance limits. Angle limits refer to the physical bone's relative rotation limit to the parent bone. We can see there are XYZ axes that can be constrained. Keep in mind that these axes directions are referring to physical bone's local coordinate axes. Local coordinate axes can be displayed here in the armature setting. Here I set this physical bone can rotate along Z-axis and X-axis. Here, we will observe the rotation along the Z-axis. After a severe shake, setting it to 90 degrees allows it to rotate by 90 degrees relative to its initial position. Setting it to 45 degrees allows it to rotate by 45 degrees relative to its initial position. Then let's look at the distance limit. Distance limit is just like the angle limit. Here I set the relative distance limit along the x-axis. Compare point 2 and point 5. We can now take a look at some settings in the scene. An important value is FPS. The FPS setting should consistent with our keyframe animation frame rate. Here we can see the Blender scene FPS is 24. Then we can also keep this value same as scene setting. If it differs from scene setting, the time speed of simulation will be different. For 12 FPS setting, we can see its time passing speed also speeds up. For 48 FPS setting, we can see its time passing speed also slowed down by half. Gravity is a force parallel to the global z-axis direction. As for these two parameters, simulation accuracy can be improved by increasing them. If you need to create a force field, we can go to this panel for creating a force field. Press plus button, then create an arrow empty object. Rotate to the angle we want. The direction the arrow points is the direction of the force field. This will apply a force to all physical bone. Then set this arrow object as the force field reference object. Then here's a factor. This factor multiplied by empty object's z-axis scaling indicates the force of this force field. Here I set it to 10. Then play to see the result. While playing, we can scale this arrow. You will see the force field change. Next, let's look at soft connections. Sometimes when we create skirts or capes, we might find that after collide, physical bone around do not move together. In this example, only 3 bones were affected by the collision. Their neighboring bones did not move. This may cause mesh stretching. To avoid this situation, we can create soft connections. Select the skirt's physical bone. Press Ctrl W. Choose 2. Adjust the spring stiffness. After apply, let's look at the result again. Besides the 3 bones affected by the collision, surrounding bones also move together. Next, let's look at additional constraints. When we simulate physical bones, you might sometimes find physical bones move exceeding the angle limits or distance limits we set earlier. This is because during physics calculation, if these physical bones are subjected to very large forces, they may exceed these limits. To avoid this situation, we can set some additional bone constraint. Here we select the skirt's physical bones and press Ctrl Q. You can set additional constraint for physical bones. After setting, press OK. We can take a look. Every physical bone has 2 additional constraints. One is a distance constraint, and one is a rotational angle constraint. Its value corresponding the value we set just now. Here we need to pay special attention to its axis, because sometimes your bones may generate bisymmetry. The axis of symmetry bones may flip. Therefore, when using this function, you should be very careful with the XYZ axis direction of bones. Incorrect bone direction will lead to incorrect constraint results. After setting, play again. You'll find even though the rigid body has been pushed away from the limit distance, but our bones are still within the constraints. This is because the effect of our additional constraints. Next, let's look at the use of tools. After you set a bone as a physical bone, you will find it can't be moved or rotated, because it set a copy transform bone constraint. This add-in used the driver object to drive bone movement and rotation. If we want to display all the driver objects, we can click the Show All button below to display all the driver objects. Hide All can hide all the driver objects. If you want to select all the driver objects, click this button. Here we can see all animation keyframes are also applied on the driver objects rather than bones. If you want to select the driver object corresponding to the currently selected physics bone, then we can select the bone and click this switch button. This will select the corresponding driver objects. We click switch again afterwards, you can still switch back to the selected bone. Here we can see there is an Enable Constraint button and a Disable Constraint button. After clicking, we can find that the bone constraint influence is set to 0. And now you can manually perform some operations on this bone. If you want to gain manual control of this bone starting from a certain frame, you can turn on the keyframe option. Turn on the keyframe option, then click Disable. Seek to the frame where you don't want to control this bone. Click Enable.